Hi, y'all. Sorry, I just now got chance of um, taking my pen and put together some problems of chapter six. So let's go briefly over chapter six. Exam number two is going to be based on chapter four, five, six, four, and five. Newton's law, basically, and application of Newton's law. And chapter six is rotation, and also there is the introduction of gravity, the gravity force. So since I was not the one teaching gravity, let me do a brief review, and I know Professor Walton went over that subject with you. But so gravity is a force, as the forces we studied before. So we have a list of forces, by the way. Tension is a force that always requires strings or cords or cables. That's tension. The other force is weight. And up to now, weight and gravity, I'd be using the same term to describe both. Um, it's it's always, or it was always applied to an object that is close to Earth's surface. And because of that, the value of gravity is given by the product of the object mass times g, 9.8. And this, I would like to expand this a little bit after we go over the list of force. I'm just trying to refresh your memory on that. So we have tension, gravity, force. We also went over friction, the two types of friction forces, kinetic and static. And kinetic friction has a specific equation for it, which is a coefficient of kinetic friction times the normal force. Okay, and the static friction is a force that has a range of values. It can be in its maximal value equal to a coefficient of static friction times the normal force, but can be zero, right? So it's somewhere in between, and we explore those possibilities in class. Which other force? Normal force. Always when a contact exists between two objects, there is what we call normal reaction, and is always from one object to the other and is perpendicular. So, um, and so basically that's it. So let me expand gravity. So if you have an object that is on top of my table, let's say I have pumpkins on top of my table here. So I would say there is an attractive force that Earth exerts on these objects given by mg, right? It's always vertical, is vertically pointing downward because Earth itself is the object that pulls on that object, that's try to bring it down to its center. This is true if it's relatively close to Earth's surface. It's not, then the value of this force will depend on the distance given by a constant times the mass of the object you're considering, right? The mass of the object you're considering times the mass of the planet the object is um, orbiting about, or the planet the object is in, divided by the square of the distance between the object and the center of that planet. So if this represents a planet, here's the center of the planet. If you have a satellite somewhere out there, distance d, the distance b between the satellite, not the planet's surface, but the center of the planet, is the quantity that goes in the equation. Okay. And m is the mass of the planet in consideration. So the nature of this force is always attractive, always attractive. So gravity force is always attracted. So once you have two masses, the force that arises between those two masses is always attracted, never repulsive, never repulsive. Okay. Now this chapter 6 also deals with rotation, and as I stressed in the last lecture, if there is rotation, there is something called centripetal acceleration. Is also called radial acceleration. Is always pointed towards the center of the rotation curve or the rotational path, and that has an expression of it: the speed square divided by the radius of this path. Okay, and a centripetal acceleration rises immediately the notion of centripetal force, which is given by the mass that is subjected to rotation times v squared over r. So let's see how these concepts come about in some problems. So let's try to get some problems going. So you are making a circular turn in your car on a horizontal road when you hit a big patch of ice. Whoops, that's no good. Causing the force of friction between the tires and the road to become zero. That's even worse, especially if the tires are not good. If the tires are bald, kind of a no tread, no nothing. That's horrible. While the car is on the ice, okay. So what happened? So here's like a circular path, and we are looking at it from the top, right? And you have a car, one wheel, another wheel. We are looking from top on, and here's the car, kind of, right? And it's going like this in that direction, but it's rotating, right? Because friction allows the car to be kept inside this path. Now, once you lose adherence, once the friction is not there anymore, this force is over. So I'm going to take my eraser and take it out. There you go. The force that keeps the car inside the track is over. So what happened with the car? So once friction is over, the car, according to Newton's third law, in fact, first law, will just keep on going with the same velocity in the same direction as it was before. Okay, so it goes in a straight line. Another example, if you are rotating, you have a string connected to a rock or so, and then you start to rotate that in a circular fashion. So once you let the string go, right? So you have some string like this. So we have a mass, and you are holding right here. This is your hand, and then this mass goes about in a circle like this. Keep rotating, right? So half period later is going to be here. And so it's rotating like that. So let's say when it gets here, you let it go of the string. So what's going to happen with this mass? Will this mass keep going along the path, or because you let it go, it's going to fall downward because of gravity, or what? Well, once you let it go, two things happen. Once you let it go, if there were no gravity, it would just keep on going tangent to that circle, right? In this direction here, right? It would go, I can't do a straight line here. It would just keep on going that way. But there is gravity, so this mass will go in that direction, but it will also curve down because of gravity. And then you have something like that. Parabola, basically. So C would be a good option in this case. Two small objects with mass m and mass n are originally a distance r apart. So let's make them m and m, distance r to the center. There you go. And the magnitude of the gravitational force on each other is F. So because of gravity, the force, the mass capital M exert on the little m is attractive and given by F big M on M. But the little mass M exert an attractive force on the big M of same magnitude but opposite direction, Newton's third law. And this, you could call this force little m on M. So the nature of these forces are such, they are attractive, same magnitude, opposite direction. Okay, very good. So what is the nature, what is the value of this gravity force? Let me drink my coffee here. So given this situation, the gravity force between those two is given to a constant 6.67 10 to minus 11 m double M, big M divided by the distance squared. That's the nature of the force. Now, if the masses are double, what is going to be the new force? Well, the new force is going to be the same g, but now one of the mass is double. The other mass is also double, divided by, how about the distance? Oh, the distance is quadrupled. So 4r, and we have to bring the whole thing square. You have to bring the whole thing square. So which means this new force is equal to g. So let's take the symbols out of the equation and isolate the numbers. So I'm going to bring one m here, capital M there. Now the denominator 4r squared is equal to 16r squared. So let me take the r squared out, and I have 2 times 2 divided by 4 squared, which is 16. So when you look at this term here, right? This term here is this term here, which is F. So the new force is equal to F times 4 over 16 is 1 over 4. And then you can find your answer here. So B seems to be a good one. What is this? Two small objects, mass. So you can play that one. You can do that one. Try to do that one. Spaceships traveling to the moon. At what point is it beyond the pull of Earth's gravity? Well, not if it's at moon. I mean, no matter what. So if you have Earth right here, right? This is Earth. And any object that happens to be at a distance r from Earth will be subject to a gravity force that is equal to g times mass of planet Earth times the mass of that object divided by distance squared. So this force will always be there. Certainly, if r is too big, which means if you go beyond the moon, if you go beyond the Jupiter, beyond the solar system, if you go beyond the galaxy, the value of this gravity force will be so negligible. Well, so negligible, you shouldn't say these things, right? So it should be negligible, not so negligible. Will be negligible that you can say, well, it's not going to matter. But, moon is relatively close, so I don't know what to say here. Let's see the options. When it gets above, no. When it's halfway there, no. When it's closer to the moon, well, when it's closer to the moon than it is to the Earth. For instance, if this is moon and this is Earth, so you have this spaceship here. So Earth is still exerting some gravity force, but the moon is also exerts some gravity force. So this is the gravity force the moon exerts on the spaceship. And this arrow attempts to represent the gravity force, Earth exert on spaceship. Okay, so C wouldn't be right. It is never beyond the pole. Yeah, I would say this is the best option. Although, I mean, if it goes too far away, the gravity is not going to be important. What is this? You have a motorcycle that goes around. What is embanked? So if you're looking at a road, usually when there is a curve, uh, the engineers responsible for the construction, they put a small angle here so that when you do the curve, you can do safely. Even if you have bad road conditions or your tire is falling apart because we don't have enough money to, change the tires, so we should be careful. Don't drive with bad tires and bad road conditions, and certainly don't go too fast. Um, so you want adherence, you want a friction to be taking care of your safety and not to let you go. And they do banked curves, so they put a little angle here. So since this problem is talking about unbanked curve, which means he's the center of that curve, and you have a car somewhere here, right? And the car is doing a curve, it's going around in a circle, okay? Which means it's going towards you. So if you're looking at the car is going towards you. This is the symbol of getting out of the computer you're looking at and going towards you. So you have a motorcycle goes around, the radius is given. Here's the radius, right? The radius, 13.7 meters. And it has a steady velocity. So, no, it's not a steady velocity, it's steady speed. Velocity is not steady because it's changing direction all the time since it's going a curve. And that is 96.5 kilometers per hour. Okay, very good. What is the magnitude of the net force on the motorcycle? So let's indicate the forces on the motorcycle. We have certainly the weight of motorcycle, which is Fg. Remember, since this motorcycle is on top of Earth, then weight is given by mg, mass times gravity. There is a normal force from the floor on the motorcycle that is balanced out by the weight. So these two forces have equal magnitude, which means they cancel out. But also it has, and this professor Kevin Walton might have gone through that with you, has a centripetal force. There's a friction force. Right here. Has a friction force. And in this case, believe it or not, this friction force is static. So your motorcycle is not skidding, right? So if you see these people doing a turn with a motorcycle, the motorcycle goes in an angle, kind of a curve down, right? Approaches the road. So the driver doesn't stay exactly vertically positioning respect to the floor. It tilts a little bit. And so the friction, which is static, if you don't understand why static, please email me or talk to me tomorrow. So this friction with the static because the tire is not skidding. It's not making a funny noise when it does the curve. This static friction is the only horizontal force acting on the motorcycle. Unless the curve is banked. And then you have normal force too, or if the motorcycle is, so that if the curve is banked, you have a complicated issue here. You have a normal force going that way. You have a friction force going like, sorry, it's not right. You would have a friction force. Oops. You would have a friction force that is going in the direction of the road. You have a normal force going that way, and You would have a gravity force vertically down, and here would be the center of rotation. So you would have to do some more complicated issue here. That's what you got. You have three forces acting on a motorcycle: the static friction, the gravity, and the normal force. Now, when you look at this three forces, which forces can you consider centripetal? What is the definition of centripetal force? So let me write here: centripetal force. Centripetal force is not a new force we are studying, okay? It's not a like tension, like spring force. It's not like gravity. It's not like a normal force. It's not like none of those, right? So what is centripetal force? Centripetal force is the net force. Is the net force that happen to be pointed, that happen to be aligned along the direction effect. Find a better way to say. Centripetal force is the net force towards the center of rotation. The center of rotation. So you have to identify around which point your object is moving. And the example I just show up here, let's see, did I do a pendulum? Yes, I did. So for instance, this object here, this mass, is circling around which point? It's not around this point, but it's around this point over here. So when you think about centripetal force, you have to find what are the forces that happen to be projected along this line. Is gravity part of the centripetal force? No. But the tension force projected along this line is your centripetal, can be added as part of your centripetal force. So let's go back here. So in this case, which force is centripetal? Well, friction. Friction is centripetal force, and that is equal to the mass of that object times centripetal acceleration. And centripetal acceleration has an expression of it, and that is v squared over r. Okay? So you have to know the mass of the object, and the mass is 250 kilograms. Okay? We have to find the speed. The speed is given, so 96 kilometers per hour. So the speed is 96.5 kilometers per hour. So we want to convert this to meters per second. So what do you do? Well, I want a kilometer to go away, and to keep it the same value, you multiply by 1,000 meters. Now you have a meters, and you can get rid of kilometers. Now I want to get rid of hours over here, but I want to cancel this. But since I multiply by hour, I have to divide by the equivalent in hours in seconds. And then I do that, right? So then I convert my speed to meters per second square and divide by the radius, which is given, 13.7 meters. And then I can have my whatever it is in Newton. Okay, this, go another one. Let's make some more obvious type of problem here. Let's see, what is this? You have a jet plane that's flying. Why do I need this? Get away. Jet plane flying 6 meters per second, experienced an acceleration is equal 4g when pulling out of a circular dive. What is the radius of curvature of the circular part of the path in which the plane is flying? So you have a, oops, see if I can line up. There you go. Nice circle, and you have a little airplane, right, flying like this. It's going that way, and then experience this acceleration when it's coming out of this circle. Circle has a radius r, right? And it's funny. I'm putting this in a plane that happens to be parallel to Earth, right? So, but anyways, what is the radius? So we want to find the radius. This is our unknown. So it is said our acceleration, in this case centripetal, is 4g, and this acceleration centripetal is v squared over r, and we want to find r. Now the speed is given, right? So then our r shall be v squared divided by 4 times g, and then we have to calculate this. We take 600 v squared divided by 4 times 9.8. So that should be equal to 5 divided by 4 and well, I don't want to invest a lot of time, but I made g equal 10 just to make it simple. This is about 9,000 meters. So I think this is the best option. Okay. How about this? We have a bead, it's right here, attached to 120 centimeters long string. So L is 120 centimeters. So this should be equal to 1.20 meters. This bead moves in a horizontal circle. Can I do that? Oh, there you go. Oops, bad. And the speed is given. So we have the speed, 1.5 meters per second. What is the tension? So what are the forces on the bead, assuming the angle 25 degrees is given? So forces I like to give in red. The forces are the weight of that bead. We have a tension, T, up there. And those are the only two forces. That's it. And we want to find tension. So if you take the projection of these forces in x and y direction, if you take your y-axis like that and your x-axis stationary like this, your tension T is given by a T y in that direction plus a Tx in this direction. So basically, in fact, let me change it. Let me change the value of this component so you know I'm not inventing forces. I'm just writing in blue the components of T. This is my Tx right here. Tx. Now, as you look at these forces, so out of the forces or projections, which ones are turning towards the center of rotation? Here's the center of rotation. O is only Tx. Tx is the centripetal force. Is your centripetal force. Is your centripetal force. And Tx is equal to mv squared over r. But what is Tx? Tx is not the tension itself. Tx is equal to what? T sine of 25. How do I know that? Well, you know, if you play around with your geometry, alpha is 25 degrees. So the angle down here is 65 degrees, right? 65 degrees. So the projection Tx is equal to T cosine of 65, which is T sine of 25. Another way of seeing that is sine of this angle, sine of alpha, sine of 25. If you look at the triangle given, sine of 25 is equal to Tx over T. And then Tx is T sine of 25. So this is T sine of 25. And then from here, we find that T is equal to mv squared over r divided by sine of 25. We know the mass, so make sure your mass is converted to kilograms, okay? Right? And then you plug it in here, and the speed is given, and the radius is given. From what height above the surface of Earth would an object be drawn to initially experience an acceleration given by that? Well, so you have mass Earth, you have some object in there, and then you drop. So as you drop the object has a force, Fg. Since it's away from Earth, it's not mg. Remember, mg is you can only use if it is on top of Earth's surface. So Fg is given by g, mass of the object, mass of Earth divided by the distance, which is the distance from the object to Earth. Interior square. Okay. So, and this corresponding to the mass of the object times the acceleration of that object, right? So you can cancel the mass. So basically the acceleration of an object that is dropped at a certain height, which the problem gives us, is equal to g mass of Earth divided by the distance to the center of Earth square. Okay. And then since g is a constant, we know since mass of Earth is given, it's right there, and g is right here. So once you plug, and g is 9.8, right? 9.8. Since you plug these quantities in the equation, you can find d. d is determined. Okay? But what d is? D is the distance from where the object is to the center of Earth, so which I'm calling r. But r is what? Is the height, which is the distance of the object to Earth's surface plus Earth radius. So d is equal height plus r. And then we can find the height, d minus r. Right, so let me indicate here better. So we have Earth, and we have a radius r. and we have the object right there, and here's height. So the whole enchilada here is what I'm calling D, and D is what goes in the equation. The radius of Earth is r, at what distance above Earth's surface with the acceleration be 4 point. It's kind of the same problem, right? So we have Earth, radius r, at what distance h? So we want to find h. What distance above Earth's surface will the acceleration be 4.9 meters per square second? So this number, 4.9 meters square second, sorry, meters. Oh boy, I think I'm getting tired. Meters per square second is equal to g, mass of Earth, divided by distance squared. And then we can do like we did last time, but you can also do something different. You can put here d, which is this whole thing here, d. You can put r plus h squared, and then you can solve, right? So r plus h is equal to square root of g mass of Earth divided by 4.9, right? And then you can find your h. Oops. H is equal to r minus that thing, and then make your calculator to work. All right, let me know if you need anything else.